Hey guys, good morning. It became a little late. I start right away. I think it will make me host. Thank you. Okay. So people, we have been seeing a lot of stuff, right? So we saw what are the different types of intermediates I can have, right? So tell me guys, if I have homolytic cleavage, what kind of intermediate I'll get? If I have homolytic, yes, right? So if I have homolytic cleavage, I will have free radicals formed. And if I have heterolytic cleavage, the other two will be formed, that is carbocations and carbanions, right? So tell me guys, what is the hybridization of free radicals? If I have a free radical, that carbon atom is what hybridization? Quick. What is the hybridization? Hello? So you forgot. There is one in the chat. Yes, sp2 Venetia, correct Venetia. Yes, good. Right. So if I have free radicals, right, they will have sp2 hybridization. I told you that single unpaired electron you should not consider as a lone pair. It is just an electron. So again, eventually you will see only 3 bonding atoms. So it's sp2 hybridized. What about carbocations?
sp2.
Yes. What about carbanions? Sorry?
sp3, sir.
Yeah. So it is sp3, right? Okay. So now we understood even the importance of why we are studying about intermediates, right? So I gave you a reaction addition of HBr to an alkene. You saw that, like if I took, I think, propene as the example, now you saw that there can be 2 types of carbocations formed. Okay, fine. Okay, tell me guys, any intermediate can be classified into 3 types. What are they? Any
Primary, principal, secondary, and tertiary, sir.
Right? So I have primary, secondary, and tertiary. It depends on the carbon possessing the charge or the radical is attached to how many other carbon atoms, right? If you see that it is attached only to 1 carbon atom, primary, 2 carbon atoms, secondary, 3 carbon atoms, tertiary. And if I have just CH3 dot or CH3 plus, it's going to be methyl radical or methyl carbocation, methyl carbanion, right? So as I told you, we took propene as the example, right? And you saw you can have either a secondary carbocation formed or a primary carbocation formed, right? And I told you secondary carbocation will be formed in majority because that is more stable, and the product also will be according to that, and that is what is called as your Markov-Nikov's rule, right? So anyways, that's where we stopped, right? Okay, so today we will concentrate on how do you decide the stabilities of different species, right? So I told you yesterday that secondary carbocations are more stable than primary carbocations. Why? Why is it that? But if I go for carbanions, it's going to be opposite. So that is primary carbanions are more stable than secondary carbanions, right? Okay, so how do we go about it, right? There are certain effects. There are going to be, actually we're going to study about electron displacement effects. So electron displacement, I think you can understand what you mean by this. Electrons are going to be not in their original positions. It is going to be somewhere, it is going to be moving. That's what you need to understand. So what are the effects, electron displacement effects you're going to study, right? So under this, the first one is what is called as inductive effect. Right, this is one of the most basic electron displacement effects, right? So again, why are we using all this? Say with the help of these electron displacement effects, I can do certain things. One is about the stability. Okay, bear with it, guys. Right, one is about the stability. The other can be acid strength. Like if I give you different acids, with the help of these electron displacement effects, we'll be able to say, okay, this is a better acid, this is a weaker acid, something like that. And also I can go about the basic strength, right? I can even talk about the basic strength of different bases. Okay, right. So anyways, we'll be these three only will be majority seeing, and if at all is there anything else, I'll let you know. Right, fine. What do you mean by this inductive effect? Right. Okay, so for us to understand this, we'll directly go for an example, people. Okay, fine. So say I have CH3, CH2, say one more CH2, and say I have a chlorine atom. Okay, I have this particular molecule with me. This is my 1-chloropropane, isn't it? Right, fine. So guys, so for inductive effect to be in the picture, if you want to see inductive effect, you need to understand that definitely there should be a polar bond, or else you will not be able to visualize this. Right, I should have a polar bond to be present. Okay, if not, you will not be able to visualize this effect. Okay, so obviously you see there is a polar bond here. Carbon chlorine bond is actually there, right? Okay, hope you remember what do you mean by a polar bond. What is a polar bond? What is a polar bond? How do you define a polar bond, people? Okay, answer this question. If I have a, fine, you tell me, what is a polar bond?
So what is the question?
I'm asking you, what is this polar bonds? What do you mean by this? When do you decide that the bond is polar? Based on what?
Based on number of electrons given to
No.
It's formed when electrons are shared unequally. Sir.
Electrons which are?
Are shared unequally between two atoms.
Okay, fine. That makes sense, right? So obviously you have to see, whenever you want a polar bond, right, I should have high electronegativity difference between the bonding atoms. Say if I have a bond like AB, right, and when do you consider that this bond can be polar? If there is sufficient electronegativity difference between A and B, if you have, right, now that is what is called as polar bond. Obviously, if you have, say for example, if B is more electronegative than A, right, so if at all, if it is not, I mean, if at all they have both equal electronegativities, this electron pair which is shared here, right, will be exactly at the center of these two nuclei, right? But if you have one atom to be more electronegative, the bond will be more towards the more electronegative, I mean, not the bond, the electron pairs or the electron cloud will be more towards your more electronegative atom. Thereby, it induces a partial negative charge on the more electronegative atom and a partial positive charge, right? Partial positive charge on the less electronegative atom, isn't it? So these kind of bonds are what are called as polar bonds. Correct. Now, same kind of situation you see here. Carbon is less electronegative, chlorine is more electronegative, right? So what is going to happen? Same thing is going to happen. Basically, I'm going to have a separation of charges happening, right? Okay. So maybe I'll make some space, right? So again, I write the compound. So I have CH3, CH2, CH2, and Cl. Okay, right. So as I told you, this bond, CCl bond is polar, right? So obviously I am going to have a partial negative charge on this chlorine atom and a partial positive charge on this carbon atom. Correct. Right. Now, is this going to end here? That's it. Is nothing else is going to happen? Actually, something else is going to happen. Right. Now, what is going to happen is now the electron cloud has moved away from this carbon, isn't it? So just to compensate that, you are going to have this bond electron cloud to be moving towards this carbon atom. Correct. Or I can say that chlorine is so electronegative, it is not only going to attract this bond pair of electron, it is actually going to attract this bond pair of electron also. That is the next carbon's electron also, right? So that is also going to move towards chlorine, right? So in that case, I will have a positive charge, partial positive charge on this carbon, but it is going to be a lesser amount of positive charge, isn't it? Now, if I compare the positive charge here and the positive charge here, here it is going to be more than what is in this case, because chlorine atom is very close to this, right? But chlorine atom is a little far away from this carbon. Yeah.
So that means even chlorine's negative charge increases, right?
No. That will be fine. That will be perfectly all right.
But if it's attracting electrons towards it, should increase, right? So.
Exactly. This electrons are going towards chlorine, or you can say, okay, pretty much it is going to increase, you can say, or this will be already compensated. Like I told you, step by step, like this first attracts, then that first attracts, but everything is going to happen in a matter of seconds, right? Okay. So eventually this will be fine. It will be higher. Yes, it will be higher. No doubt about it. Right. Okay. So again, I can say that even this carbon atom will get affected because of the presence of chlorine atom, right? So I would say here also I might have a partial positive, but it is going to be very, very less compared to this again, right? So if at all I had one more carbon atom, I would say after 3-4 carbon atoms, the partial charges are going to vanish. There's not going to be any partial charge, right? So why do I call it as inductive? This is what is called as inductive effect, people. Why is it called as inductive effect? Inducing effect. What do you mean by inducing something, right? Say for example, you are a good guy, right? Say you make friends with a bad guy. He is going to induce all the bad qualities he has on you. And same way, the other thing can also happen. You have some good qualities. You might induce the good qualities onto him. So either way, it can happen, right? So that is what is called as inductive effect. Or say, there are a group of 5 people. Or say, like I don't want to take people into example. Say there's a box of 5 apples, right? So even if one of them is spoiled, after a point of time, you'll see all the 5 actually will get spoiled, isn't it? So just because of one, all the other things are getting spoiled. Just like that, because of this one polar bond, I have, all the other carbon atoms are actually getting affected, right? So this is what is called as inductive effect. Okay, now guys, right? So inductive effect, what you have to understand is going to be distance dependent, in the sense that you can see chlorine atom is very close to this carbon, so higher positive charge, a little far away, lesser positive charge, still more far away, still lesser positive charge. After 3-4 carbon atoms, there will be no positive charge, negligible positive charge, right? So as you move away from the polar bond, right, the amount of partial charges are actually going to decrease. Correct. So what you have to understand is this is going to be distance dependent. Very important point. Inductive effect is distance dependent. You have to remember that. Right. Fine. So how am I going to use this for stability? Okay. Now please understand, people, right? For stability criteria with respect to inductive effect, stability, right? Stability is inversely proportional to the amount of charges present. Okay, like don't compare this with this statement which I told you. Let me just give you an example for this, right? This you remember. Okay, so less and less is the charge. I will say more and more neutral the species is, right? More and more is the stability. Okay, so this can be used again. One more thing is you can use inductive effect only for charged species. Right now, tell me which intermediate I will not be able to use inductive effect. Given that statement, all the statement I told you, this can be used. Inductive effect can be used for only charged species. So, which intermediate I cannot use here?
Carbocation and carboanion.
We can use only carbocation and carbanion. We cannot use free radicals because free radicals are not charged. They are neutral species. Correct? Okay, so I can use inductive effect for deciding the stabilities of different carbocations, different carbanions, but not for free radicals. Okay, it is not gonna work for radicals. Please remember that because they are not charged. Okay, right, fine. So okay, now for us to understand an in-depth inductive effect. Okay, now what you have to understand is there are going to be something called as electron EWG, okay, and EDG. Okay, what is this? Right, EWG is electron withdrawing groups, and EDG is electron donating groups. Okay, EWG, electron withdrawing groups, and electron donating groups. We have to understand what are they. Okay, so I can understand, right? Electron withdrawing groups are going to be more electronegative. Can I say that? Right? They are going to pull the electron cloud towards themselves, right? And electron donating groups are going to be opposite. They're going to donate electron to the other species. Okay, now in this case, the example which we took here, right? So I would say this chlorine which I have here is actually an electron withdrawing group because you see it is going to withdraw electron towards itself. Right, so that's an example for an electron withdrawing group, right? Fine. So let us list out what are all the electron withdrawing groups I can have, what are all the electron donating groups I can have, right? Okay, so electron withdrawing groups example can be say X minus in general, any halogen for example, right? So X minus, that is Cl minus, Br minus, F minus, I minus, all these things, right? Okay, and say I can have any. Okay, I understand what you mean by electron withdrawing groups. Hopefully, right? Say I can even have, if at all in the this thing, if you have a OH, that again will be an electron withdrawing group, right? Say if I have even a carbonyl compound, C double bond O, that will be an electron withdrawing group, right? What else? Anything which is electronegative. Now, how can I say this is electronegative? I told you this carbon atom is sp2 hybridized, right? Or whenever you have a double bond. So obviously, when the amount of s character increases, right, the electron negativity of the carbon increases. Or you can see it in this way also. I have this oxygen, which is highly electronegative. Again, because of that, I can have electron withdrawing power, right? Okay, so like this, I can have so many other things which can be electron withdrawing groups. Okay, even I can have cyanides, right? Even NH2, or any electronegative atom, even this carbon is sp2 sp hybridized. Again, that will be more electronegative than this also. So anyways, right, so all of these can be electron withdrawing groups, right? And electron donating groups, you don't have many. All alkyl groups are actually going to be electron donating groups. Say for example, CH3, C2H5, all these things are going to be electron donating in nature. Okay, right? So this you have to like not have to remember. There's nothing to remember. It's purely logical, right? But electron donating groups are going to be all alkyl groups, RCH3, C2H5. All these things are going to be electron donating groups. Okay, now when I go for electron withdrawing groups, people, right? What you have to understand is which if I give you two things, if I give you two electron withdrawing groups, which will have more electron withdrawing power, that also matters, isn't it? Say for example, if there is an IF and there is an iodine, right? Tell me which will be more electron withdrawing. If I have fluorine and iodine, which is more electron withdrawing?
Fluorine, sir.
Obviously, there's no doubt, because fluorine is more electronegative than iodine. The electron pulling power of fluorine will be far, far, far greater than when compared to iodine. Right? So it's all based on difference in electronegativity. Whichever is going to have more electronegativity, that is going to have more electron withdrawing power. Okay, fine. Now, based on whether I have electron donating group or based on whether I have electron withdrawing group, this inductive effect, right, can be plus I effect or it can be minus I effect. There are two types of inductive effect. Okay, plus I effect or minus I effect. Right, now, what do you mean by plus I effect? What do you mean by minus I effect? It's pretty simple. Now, plus I or minus I is we are gonna talk with respect to carbon only. Okay, plus I or minus I, we are going to speak with respect to carbon. Okay, so when I say plus, right, I am going to have carbon to mean what to say, the electron cloud is going to be increasing towards carbon, or say the electron cloud is going to move towards carbon, right? So what kind of groups can give plus I effect? Tell me. Again, I repeat, plus I effect means the electron density or the electron cloud on carbon atom will increase. Okay, so tell me, electron withdrawing groups or electron donating groups will give me plus I effect?
Electron donating group.
Obviously, right? So if I have an electron donating group here, this will donate electron to carbon. So the electron density on this carbon atom will increase, right? So that is what is called as plus I effect. So electron donating groups will always give me plus I effect, right? And obviously minus I, that means the electron density on carbon decreases. So whenever you have carbon atom attached to an electron withdrawing group, that will decrease the electron density on the carbon. So that is what is called as your minus I effect. Okay, so electron withdrawing groups always gives me minus I effects. Okay, so these are the basics now, right? This and all, if you know, now we can directly go for your stability criteria. Okay, and please remember, people, stability, I told you, this is for inductive effect. There is only one stability criteria, that is stability is inversely proportional to the amount of charges present on the species. Okay, more and more neutral it is, more and more is the stability. Please remember this. Okay, I obviously have to remember what are electron withdrawing groups, what are electron donating groups, plus I effect, minus I effect. If we understand, we are set to go for the examples. Okay, fine. Now we actually started all this to decide the stabilities of intermediates. Okay, so let us take the example. Let me take a primary, secondary, tertiary carbocation, or methyl also I'll take. Say now I'm going to take 4 species. One is this CH3 plus, say other thing is CH3, CH2 plus, say I have CH3, CH2, I mean not CH2, CH, CH3, say there's a positive charge here, and say another one, CH3, C, CH3, CH3 plus. Okay, so obviously you can understand this is methyl carbocation, this is primary, right? This would have been secondary, this would have been tertiary. Correct, right? All these are carbocations, right? Now we are going to decide which is more stable, which is less stable. All these things we are going to see, right? Now remember the criteria. Criteria is less charge, more stability. Okay, less charge, more stability. That means out of these carbocations, whichever is having the least amount of positive charge, okay, that is going to be the one which is going to be maximum stable. Again, I repeat, the out of these four carbocations, whichever is going to have minimum amount of positive charge, all these are positive charges, minimum amount of positive charges, that species is the most stable one. Okay, now we have nothing else but to use inductive effect for now, right? Now I told you, you have no other groups here. You have just alkyl groups present. You can have just CH3, 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 CH3. All these are alkyl groups, correct? And these are the species, the carbon atom is having a positive charge, no issues. Okay, right. Now I told you, alkyl groups are what kind of groups? Alkyl groups are what kind of groups? Just now I told you. Electron withdrawing or, oh, there is somewhere in the chat. I didn't see it. What is first film, Nitin? Mass. Okay, fine. So what I was asking, so yeah, what kind of groups are they? Alkyl groups. What kind of groups are they? Just now we saw it.
Donating.
Yes, you can see here, right? You can see all electron donating groups are alkyl groups. R represents an alkyl group, CH3, C2H5. All these are electron donating groups. Please remember. Okay, right, fine. So if that's the case, right, if that's the case, there is no electron donating group here, so we don't have to worry about it, right? Now in this case, I have one electron donating group, which is going to donate electron to this carbon. Right, now in this case there are two electron donating groups, this side and this side. Right, now there are three electron donating groups, this side and this side, all donating electron to the carbon, a carbocation, the carbon having the positive charge. Right, now tell me guys, if I have an electron donating group like this, right, what is going to happen to the amount of positive charge? Tell me, will it increase or decrease? If I have electron donating groups like this and I have a positive charge, right, will the amount of positive charge increase or decrease?
So could you repeat the question?
What I have is there is a positive charge here. Okay, that I understand. And what I have here is a methyl group, which is an electron donating group. Electron donating to what? Electron donating to this carbon. Right. So what I'm asking is, if I have a positive charge and if I have an electron donating group like this, what will happen to the amount of positive charge? Will it increase or decrease?
Decrease.
Decrease, right? Because electrons are negatively charged, right? And you have a positive charge here, and you see this is an electron donating group. So obviously the amount of positive charge decreases. Guys, everybody understood how the amount of positive decreases? Please give me a S.
Yes,
right? Okay, one S, guys, please be proactive. Did you understand? How is it that the amount of positive is decreasing on this carbon? Everybody understood?
Yes, sir.
Okay, two. I think that is Venisha. Yes, three. Others? I have seven people here. Bavadarni. And I have, oh, I think Bavadarni only said now, right? Mithun, Rahul, Shruti. I don't know whether it's Shruti or Bavadarni. Whoever said yes.
It
Sorry?
was Shruti, sir.
Oh, it was Shruti. Okay, Shruti. Sorry. Right? Okay. Okay, Abhishek also said yes. Okay, fine. Hope you guys understood. Fine. So because it's electron donating group, the amount of positive charge will decrease. Okay. Now, when I compare this carbocation with this carbocation, a primary carbocation, you can blindly say that which is more stable. If I compare this with my primary carbocation,
the primary carbocation.
Absolutely. Now, just now I told you what is the stability criteria for, sorry. Yeah, what is the stability criteria? Lesser charge, more stability. Now, because of electron donating group of CH3, the amount of positive charge decreases. Now here I don't have anything. I don't have an electron withdrawing group. I don't have electron donating group. So the amount of positive charge, whatever is there, is going to be there, right? There is nothing to decrease it. So definitely primary carbocations are more stable than methyl carbocations. That is for sure. Right. Okay. Moving on to secondary. Now, I think you'll be able to understand there are two electron donating groups, both coming from either side. Right. So, can I say the amount of positive charge will be still lesser than in the case of primary? Right. Because there are two electron with donating groups here. Right. So, where am I going to have lesser positive charge? Obviously, in secondary, I'm going to have lesser amount of positive charge when compared to primary. Because in primary I have only one electron donating group, but in secondary I have two electron donating groups. When I go for tertiary, that is going to have still more lesser amount of positive charge because I have three electron donating groups, right? Okay, so where do I have the least amount of positive charge? It is going to be in tertiary, little higher secondary, little higher primary, and with the maximum amount of positive charge is going to be with the methyl carbocation. Right. Okay. So keeping all this in mind, now I think I'll be able to directly give you the stability order of primary, secondary, tertiary, and methyl. Now, wherever I had the least amount of positive charge, that is tertiary, that is the most stable species, meaning that is the most stable carbocation among these four. Right. Now, then comes secondary, then comes primary, and then comes your methyl carbocations. Okay, now this is the order of stability for your carbocations. Tertiary is more stable than secondary, secondary is more stable than primary, and primary is more stable than methyl carbocations. Okay, this you will not remember, it's pretty easy, it's just logical, it's purely logical. Okay, now if it was not carbocations but carbanions, people, right? Okay, just take that. Say if I have, again, I'm just going to take all these four again, but in the form of negative charges, carbanions I'm going to take. CH2 minus. Minus, right? Okay, again, methyl, primary, secondary, and tertiary. Right now, again, nothing is going to change. Again, I still have only electron donating groups. Right now, tell me, guys, if I have an electron donating group attached to a carbanion, what will happen to the amount of negative charge?
Increase.
Exactly, right? These are electron donating groups attached to a carbanion. So obviously the amount of negative charges will increase if I have electron donating groups, right? Okay, now in this case, I don't have any electron donating or electron withdrawing group, just methyl is there. Now here you have one electron withdrawing group, so increase in negative charge. Two electron withdrawing groups, still more increase in negative charge. Three electron withdrawing groups, still higher negative charge. Right, now tell me, what is the stability order? What will be the stability order? Same criteria, lesser charge, more stability. Now, which has the least amount of charges here?
Primary, sir.
Primary or before that?
No, before only CH.
Correct. So I'm going to have methyl carbanions to be the one which has the minimum amount of negative charges, right? And then comes primary, then comes secondary, then tertiary. So in case of carbanion stability, CH3 minus is the one which is more stable. Then comes the primary, then comes secondary, then comes tertiary, right? Because tertiary has 3 electron donating groups increasing the negative charge on carbon. That has the maximum amount of charge. So that is the one which is least stable. Okay. Now, obviously, you can understand it is going to be exactly opposite of when I compare it to your uh, carbocations. Right? Okay. Right. Fine. Now, let us take some more examples. Right. Okay. Say, if I have okay, fine. Let me compare these two. Okay. Now this is structure number 1. This is structure number 2. Right. Now tell me, guys, which is more stable, 1 or 2? Let me take a vote. Okay. So how many of you say, or just put it in the chat box, which do you think is more stable? Look at the structures. Okay. So these are the structures. Structure number 1, structure number 2. Both are carbon ions. Okay. Fine. Now think, and just everybody has to participate, right? Now put it in the chat box. What do you think? Whether 1 is more stable or 2 is more stable? I'm looking at your chat boxes. Or unmute. You can unmute yourself also and speak.
I think 1 will be more stable.
Okay. So 1 vote for 1 is more stable. Then others. Okay. There is 1 in the chat. So Abhishek says 1. Okay. Others. 2. I got. Okay. 3. 3 for 1.
1, sir.
Okay. 4 for 1. Manisha says 1. Okay, so everybody says 1. Anybody wants to tell me why are you saying 1?
So here chlorine has the highest electronegativity, sir.
Okay.
So it will take an electron latine polarity with the other 2 carbon. So CH2 will get a partial positive charge, and then CH2 minus will also get a partial positive charge and be balanced. In second also the same thing happens, but the positive charge will be less in second because
understood. I understood what you're telling. Thank you, Rohan. Right, almost correct the way of explanation, but you don't have to go for partial positive charges here because I already have a negative charge. Right, I already have a negative charge. So telling that here I'm going to have partial positive is not correct. But yeah, the explanation is almost 99% correct, except that you told there is a positive charge. Right. So what you have to understand is, people, here there is a chlorine atom in both of them. Right, and obviously chlorine atom is going to be an electron withdrawing group. Correct. So if it is electron withdrawing, so obviously the simplest way of explanation is I have an electron withdrawing group, so the amount of negative charge will decrease. As simple as that. Electron donating group increases the negative charge, electron withdrawing group decreases the negative charge. Right. In both these cases, the amount of negative charge is decreased because of the presence of chlorine. Right. The next question is where it is more effective. Now, I told you that the inductive effect is distance dependent. As and more closer it is, more and more stronger effect it will have. Right. Now, here you see this is just 1 carbon away. Right. Now, in this case, this is 2 carbon atom away. So obviously here I'm going to have more effect pronounced than in this case. Right. So obviously where I'm going to have lesser negative charge, here only I'm going to have lesser negative charge because the chlorine atom is little closer. It is going to have more effect electron pulling. Right. So but than in this case, it is 1 carbon atom away, or I would say even 2 carbon atoms away, however you want to consider it. Right. So obviously 1 is more stable than 2. Okay. Most of you got this. Very good. Very good. All right. Next example we take. Say if I had Now structure 1 and 2. Again, we'll take a vote. Okay. How many of think? Okay. What do you think? Which do you think is more stable? 1 or 2? Again, we'll take a vote. Now this is the carbocation. Do not go for partial positive charges, then it will become a little confusing. Yeah, tell me. What is it? 2. Okay, so 1 vote for 2. Okay, others.
2, sir.
Okay, again 2. 2 votes. What do you think, others? It's just a guess. Okay, I'm just checking how good your guessing is. So 2 votes for 2. Others. Yes, please participate. I'm looking at the chat box if you want to put it in the chat box. Quick, guys, we don't have time. Quick. 1 or 2. Okay, I don't know what is the problem. I don't want to waste time. Okay, so yeah, your answer is correct. 2 is the one which is going to be more stable. Yeah, right. So how do we decide this? Now it's a positive charge here, right? Now tell me, guys, if I have a positive charge and an electron with the drawing group like this, can I say the amount of positive charge will increase? That will destabilize the carbocation. Is it not? Electron donating group, if I have, wonderful. Yes, it is going to stabilize the carbocation because it is going to decrease the amount of positive charge. But if I have an electron withdrawing group, right, now that is actually going to increase the amount of positive charges. Because already it has less electron of positive charge, but because of this, still more electron are going to go towards this carbon atom, and from this carbon atom to this fluorine atom, right? Okay, so thereby I can definitely say that the amount of positive charge. So if I compare it with just your CH3, CH2 plus, this is a normal primary carbocation. This is the one which is going to be maximum stable among these four, among these three. Why? Because I just have an electron donating group here, but here I have an electron withdrawing group. Okay, right? So it's pretty easy, isn't it? So now the next question is, where is it going to be more effective? Right? Where is it that I'm going to have, say, lesser amount of positive charge, and that is where it is going to be more stable. Now, wherever I have a less powerful electron withdrawing group, again, I repeat, wherever I have less powerful electron withdrawing group, there the amount of positive charge is going to be lesser. Yes, right? Now, fluorine is more electronegative, chlorine is less electronegative. So obviously the electron pulling power of fluorine is going to be higher. That means more and more amount of electrons are going to come towards this, and little lesser amount of electrons are going to come towards chlorine because chlorine is less electronegative. Right? So where do I have lesser positive charge? Obviously in 2. In this case, 2 is more stable than 1. Right? So hope I understand how we are going to use inductive effect. Very, very easy. If you just understand what is electron withdrawing group, what is electron donating group, and obviously positive and negative charges, lesser more stability, lesser amount of charge. That's it. This, if you remember, you are set for understanding any kind of problem. Okay, right? Fine. So yeah, and inductive effect can also be used. This is one of the applications of inductive effect, deciding the stabilities of carbocations and carbanions. Now, other thing is deciding the acidic strength and basic strength. Okay, what is the time? Okay, we'll continue. I'll just take 5 more minutes. Right, fine. Now, how am I going to decide the acidic strength? With the help of inductive effect. Now, same criteria, right? Now, we know what is the criteria for acidic strength. Hope you remember. Acidic strength is direct or inversely proportional to the stability of dash. What is the dash? Stability of Stability of, if I have an acid, it will be more acidic if dash is more stable.
Positive charge, sir.
No. How do you say positive charge is more stable? Remember the example of HClO, HClO2, HClO3, and HClO4. What was the criteria there? I obviously said that HClO4 is more stable. I mean more acidic. Sorry, HClO4 is more acidic. Based on what I said that? There must be one at least to remember this. Acidic strength is directly or inversely proportional to this. I mean, sorry, it's not inversely proportional. I'm really sorry, guys. It's directly proportional. Right. Okay. Right. Acidic strength is directly proportional to the stability.
CB, sir.
Yes. What is it, CB? What is it, CB? CB? Acid? CB? What is CB?
Conjugate base, sir.
Thank you so much. Yes, it's going to be the conjugate base, right? If the conjugate base is more and more stable, then I would say that the acidic strength is higher. The strength of the acid is higher, right? Okay, so this is the criteria. And you can, if at all you know how to decide the stabilities, again, it is going to be this stability of the conjugate base is again inversely proportional to the amount of charge. This comes from the inductive effect, right? So now you can see how inductive effect and acid strength can be connected, right? So if you have an acid, remove the H plus. Now you have the conjugate base. Now use inductive effect to decide whether that is stable or not, right? And obviously you'll be able to understand, which is like depend. If I give you two acids, right, make the conjugate bases. In whichever conjugate base I'm going to have lesser amount of charge, that is the one which is going to be more acidic. Okay, right, fine. So we'll keep this in mind. This is a very important statement. Okay, so acidic strength is directly proportional to the stability of the conjugate base. And obviously, how do you say the stability of conjugate base? With respect to inductive effect. This we already know, that is inversely proportional to the amount of charge that conjugate base possesses. Right. Okay. Now we will take some examples. Right. We know carboxylic acid. The best example I can take now is carboxylic acids. Okay. Right. Now, say I have HCOOH. And say I consider with it, this is my formic acid. Formic acid is found in ant bites, right? Fine. So now I compare it with CH3COOH. Okay, I want to understand which is more acidic, right? Okay. Now, whatever first thing, whenever you are given an acid, and you are asking you to decide the acidic strength, first thing you will remove is the H plus, because you're going to check the stability of the conjugate base. Okay, hope you remember what is the conjugate base. After removing H plus from the acid, whatever is remaining is what is called as a conjugate base, right? So if I remove H plus from both of them, I will have HCOO minus. Let me write it like this. Okay, and here I'm going to have CH3COO minus. Okay, right. Now, I will tell you the answer, but can you guess which is more acidic, formic acid or acetic acid? From what you know from inductive effect. So the criteria is lesser charge, more stability. Okay, out of these two, which is having lesser amount of negative charge? And whichever is going to have lesser amount of negative charge, that particular acid will be a stronger acid. Which do you think is going to have lesser amount of negative charge? First or second, HCOO minus or CH3COO minus?
I think CH3CO
will have lesser or higher?
have higher, sir.
Higher amount of negative charge. Okay, makes sense, right? So obviously it's pretty simple. I know this is an electron donating group, alkyl group. CH3 is an electron donating group, which is going to increase the negative charge on this, right? Which is going to increase the negative charge on the oxygen, right? Because it's an electron donating group, and here I just have hydrogen. I don't have anything else. Hydrogen, I cannot say whether it's electron withdrawing or electron donating. It's nothing. It's just hydrogen. Right. So obviously I see the amount of negative charge is increased in the case of CH3CO minus because CH3 is an electron donating group. Right. So now which is a better acid? Obviously HCOOH is a better acid when compared to CH3COOH. Right. Again, I repeat what you did. Any acid given to you, first thing you will do is make the conjugate base by removing the H plus. That you're done. Now, after doing that, use inductive effect. Look at what are the groups attached to the COO minus. Every acid will have COO minus. This is also having COO minus. Right? So every acid will have COO minus. Now use the inductive effect. Look at what groups are attached to the COO minus. If it is electron donating group, obviously there is an increase in negative charge. If it's an electron withdrawing group, there will be a decrease in negative charge. And wherever I'm going to have lesser amount of negative charge, that is a more stable conjugate base, and the corresponding acid will be a stronger acid than the other ones. Everybody understood? Yes? Yes, understood? Guys, there was something in the chat.
Understood, sir.
Okay. Oh, there was something in the chat. Okay, conjugate acid, formic acid is more stable. Yes, Manisha, good. Yes, I hope everybody would have understood. Pretty easy. Now, what is the time? I will just take one more example and we'll complete it. That's it. I'm not going to take much of your time, guys. Right. Say, if I have okay, now 1, 2. Quickly tell me which is a better acid.
H3COOH, sir.
Yeah, it is CH3COOH. First one is CH2C and COOH.
Answer is 2, sir.
2 is more acidic than 1.
I think so, sir.
Okay, fine. Anybody else? One vote that 2 is more acidic than 1. What others think? Oh, wait, I'll just make the. Yeah. So now you can tell me. Guys, there was one vote that Rohan says 2 is more acidic than 1. Anybody else has a different view, or you want to say, yeah, that is correct? Oh, yeah, there is some.